Okay, I guess we're going to begin here. Hi, my name is Earl Philhauer. I work for Virident Systems Incorporated. Email and other information will be in the PDF, since it seems to be blocked by my multi-monitor. I do apologize for it. This is a borrowed laptop. But today I'm going to talk about using storage class memory to really enhance the performance of in-memory computing, something that Virident has been working on for about 2.5 years now. We just had a GA of our MySQL and our Untitled products on it. I'm really excited about it, and I think it's something that you should be excited about as well. Earl? Yes? The microphone? I certainly can. Is that better? Yeah. All right, thank you. So, basically, I'm going to tell you a little bit about Virident, but I'm going to try and keep the marketing stuff to a minimum. It says marketing manager, so I need to give a little bit of it. We're going to talk about what storage class memory is. It's kind of a new technology, kind of a new architecture. It's fitting into a new spot in the server. You might not be aware of it, but you're going to want to. I'm going to talk about a lot of the stuff that we've learned. The prior presentation, there was a whole lot of performance optimization, little hints. A lot of those optimizations aren't necessary anymore if you've got the right hardware. And I believe we do. And I'm going to talk about what Virident has done inside MySQL, inside the InnoDB, to achieve up to 70 to 100 times the performance of standard disks and well over 10 times the fastest PCI Express SSD for some Web 2.0 type queries. And I'm going to justify why that's possible and why that's unique. I'm going to talk quickly about what we've done with Memcached, which loves memory and the fact that we're talking storage class memory. That's going to be great. And basically a few other applications where we're looking for your input as well, as far as what are the interesting things to do with all of this. And I want you to get you excited, because every day I go to work and I work with servers between 256 to 512 gigabytes of memory, and I feel kind of constrained on my little laptop of 2 or 4 gigabytes. So Virident, very quickly, our marketing logo, our vision is smart scaling the internet data center. What that means is that we've got a series of appliances that we believe fit somewhere between the traditional, bog standard server and the very, very high-end, esoteric, exotic servers. Right here, these are our 2 products that we just announced, Memcached and MySQL servers. I'll talk about them quickly, but I'll talk more about the technical details later. We're about 2.5 years old. We just did a GA announcement this Monday, and this is kind of our coming out party at the MySQL conference and the Percona conference for Virident Systems as a product. So we've got a whole bunch of ex-Sun people, which is kind of sad, but there's a whole lot of ex-Sun people around now. Okay, so our 2 products right now are the Memcached server, which in a single 1U box on the left, we can easily accommodate 512 gigabytes of memory. And we do that using our own custom ASIC, custom hardware, as well as operating system changes which allow us to actually access that memory at memory speeds, not at disk speeds. The MySQL box on the right, that's a 2U guy. We use 2U simply because we want to have some SAS drives in there for redundancy and backup, and people still like their disk drives. Nothing wrong with it. So what is storage class memory? I've said it probably 20 times right now. Storage class memory is large. What that means is that everything you think you know about disks, you can kind of apply to this kind of memory. 512 gigabytes are available today in that 1U. With the next shrink of the memory technology we're using, that doubles to 1 terabyte in a 1U. Beyond that, sky's the limit as we start looking at the future technologies. But today, 512 gigabytes is running, or was running actually on our show floor. SCM is also persistent. So DRAM, you turn it off, you turn it back on, oops, all your data's gone. Because this is storage class, we're talking storage kind of like a disk, kind of that disk mentality. It's persistent. It means that the data's always there. You put your database on it, you have a power outage, you turn the power back on, the database is still there. That's one of the key technologies. There's no things like warm up, no big issues of that sort.
For how long?
For
how long can the power be off?
Well, I think that's spec to retain either 10 or 30 years. So hopefully you can get your power back on before then.
So it's not a battery backup?
Oh, no, this is not battery backup. I'll talk about the technology. It's a different type of flash than you're probably used to right now. But there are other technologies that support this as well. And they're kind of coming online right now. The other key here is it's randomly accessible, just like DRAM. DRAM, you want a byte anywhere inside that whole, 4 gigabytes or whatever you have in your laptop, your processor just has to read that byte. For an SSD, I don't care whether it's on a SATA, a SAS, PCI Express, whatever, you're going to read a whole big old block of 512 bytes to maybe 4K if you're doing an ext3 file system, even if you only need a little bit. SCM, on the other hand, is memory. It's randomly accessible. That means that you don't have to read any extra data. And we're going to go into that quickly on the MySQL optimization. And that read-ahead comment that was made earlier, you don't need to do that anymore if you get this. That's kind of one of the amazing things here. Was there a question? Or okay. And the other key is occasionally it's asymmetric. This depends on the underlying technology. Everybody knows flash writes slower than DRAM. There are ways around it, but you need to be cognizant of that. Going forward, when we look at technologies like PCM, which I'll go into quickly, that asymmetry kind of disappears, and you don't really have to worry too much about it. But it's something to be cognizant of. So how does Virident use storage class memory to make these servers that can do magic? Do this amazing performance? Well, we develop storage class memory. We're not a memory vendor. I mean, we work with the top tier memory vendors. We've announced licenses with 2 of the top flash guys. But we don't sell flash. We develop the applications. We've customized Memcached, we've customized the NODB portion commercial of MySQL, but we're not just selling an application. We're selling the combination of the two because we've had guys in our labs working with this stuff for 2 years now, getting the right optimizations, getting things balanced. Because once you start putting this much memory in a server, it's hard to use it all if you're not careful. So the idea here is we're trying to give a systems value, not just a point value. So everyone loves SSDs. I love SSDs too, don't get me wrong. They're still disks, and disks are not memory. They're never going to be memory. That is true even if you do something like a memory map, or use a swap file and put it on your SSD, which may or may not be a good idea depending upon the right lifetime. People are exploring that for virtualization. The problem there is that memrap and swapping, they use kind of operating system level tricks to pretend that you've got this memory. You don't really have this memory. Some accesses are already in DRAM, they're cached, they run DRAM speed, 100 nanoseconds. You can get your data like that. What happens when you miss? When you miss, you've got to go off and read that SSD. Sure, the SSD is maybe 10 or 50 microseconds, maybe 100 microseconds. Compared to 100 nanoseconds, that's 3 orders of magnitude away. That's a very significant number. And that actually unpredictable latency is something that we were really struggling with when we were just starting out, especially in Memcached. There's lots of these big global honking locks. We hate them, but they're there. What happens if you actually hit one of these bad pages when your application has that lock? Other threads of operation are going to be stuck behind you. It's kind of a backup effect, like on the highway. Some guy in front of you going slow, so everybody else has to go slow. And that's kind of the issue with using SAS or SATA SSDs, even PCI Express with swap. So, I've been very generic. What are the nitty-gritty details? So, DRAM's great. This is kind of an eye chart. I do apologize. But the key points here: the read and write performance DRAM, 100 nanoseconds, maybe 10 gigabytes a second if you've got a nice memory system like the new Core i7s. And read-write are basically exactly the same. And then on the other side, you've got NAND, SSDs, where people are pulling up the bandwidth, but the latencies are still, the underlying technology is kind of stuck at 50 microseconds, 100 microseconds. Between the two, inside that green circle is where storage class memory lives. It's attached directly to CPUs. And in fact, in our implementation of this, we have a storage class memory controller, the Virident Green Gateway, which sits inside an Opteron socket and speaks hyper transport. And going forward, we're going to have, we have an Intel QPI license. QPI is the interconnect for the Core i7 and all of those other server class cores coming out from Intel right now. So the key is it sits right there on the processor side, not on the other side of that I/O bottleneck. So NOR flash is different than NAND flash. NOR flash is randomly accessible. It's used a lot in cell phones. If you've got code to execute, it's like execute in place. NAND flash is very much block based. You have to read that whole block out like a disk, and it's very hard to execute code out of stuff like that. PCM going forward in the future, I know Mnemonics is talking a lot about this, and we're talking with Mnemonics. And this is a very, very exciting technology. It's still in the development stage. We do have an instance of More Flash running today. So why do you care? Well, I've got a quad core at home. This laptop probably has 2, and your servers are going to have 6 cores per socket. How are you going to keep data flowing into them? If you've got a database right now, you're probably sitting there with half your CPUs idle because you're waiting for I/O. That's a big deal. Storage class memory, the capability of storing maybe your entire disk subsystem in memory, means that you can keep those processors working and not waiting for I/O. That's the key. It narrows the distance from the CPU to the data. It makes the data available per CPU a lot larger too. I mean, 512 gigabytes is a lot of memory. I think so. And it decreases for some applications. Some applications you're sharding because you want to keep things in DRAM for your MySQL databases or whatever. You want to keep your hot set in DRAM. And you can only economically purchase, say, a 32 gig server today. So you're going to shard it maybe 32 gig or 50 gigabyte partitions and buy 3 or 4 or 5 servers. What if you could put all of that data immediately accessible memory in one box? Would that not make your life a lot easier as far as sharding? Is there a question? Or?
I just said always 2 boxes.
Always 2 boxes, agree. You know, I hear you. I hear you. Okay, so we'll get you down to 2 boxes. But that's the key there. Sharding is, you're fixing a problem that you don't really need to fix anymore. So that's the key here. And memory per system ain't shrinking. Performance requirements aren't going down. And we got to do more with less. The economy is at the tanks. You don't want to be buying servers that you don't need. And data center power and cooling. It is Earth Day. If you can consolidate those 5 shards into 2 shards, or into 2, you copy, one hot, one backup. You're going to save a lot of power right there. So why not just, get a head start on the problem? You're going to have to fix it sometime. Let's fix it today. Do it right. Table stakes, and you're going to laugh at the first point, 64 bits. But I'm sure that you've all seen people running 64-bit Linux, 32-bit apps, and using the rest as disk cache. That's just not going to fly anymore. People here probably, this is not an issue. The rest of the world, maybe so. Multi-threaded and scalable. Again, you've got a lot of memory. The processors are fast, but they're not accelerating as far as gigahertz as fast as they were. What they're doing is they're multiplying these processors, so you need to be able to do very good multi-threading. You need to be scalable, and that's not the same thing, unfortunately. No new global mutexes. Anyone working on InnoDB or the MySQL database knows about this. And the other thing is, the fact that there's no I/O means that you're going to find other bottlenecks, and you're going to have to fix them sometimes. And the final point, in some instances, the read and write speeds are not the same. So if you're used to reading and writing at DRAM speed, you may have to actually re-architect the solution slightly so that your writes go in one way and your reads come out another. And that's actually what a lot of the work that we've done at Durden has been doing, or has been involved in optimizing, finding the exact balance between the two. So kind of the rules we've developed to kind of live by, and these are good for us, and these are good for, I think, the rest of the world too. Put all your data in storage class memory, because even if you're hitting an SSD, you've got 100x performance drop. If you can't fit all your data in memory or inside storage class memory, you should at least put all the hot set if you can identify it. Read only what you need. The read ahead of 8 megabytes a second, don't be doing that anymore if you've got storage class memory. It's not necessary. If you only need a byte, if you only need a row of a database, just read that single row. Don't read 16 kilobytes, don't read 8 megabytes. You're wasting your time. The other key here, and there's nothing wrong with Linux, it's just sometimes, you've got that kernel user transition going too many times, you spend all your time doing context switches and not doing real work. If you can get everything done in user land, which is one of our optimizations for InnoDB, you're going to be a lot faster. You're going to be wasting a lot less of your CPU cycles. And you have to be cognizant of that asymmetry and be able to work it into your application. Sometimes it maps easily. Database is 90-10 read-write workload. It's fine. Others, memcache with lots of sets and few gets, maybe not so fine. You need to look at that balance. Okay, so what have we done with InnoDB? InnoDB, we've taken a MySQL Community Edition. We've taken the InnoDB. We've got a license for the commercial edition. But InnoDB, we're 5067, I think, of MySQL. And the problem is, you know, you use the Google, you use the Percona patches, you use whoever's patches. MySQL, then multi-thread's great. The problem is that you're still going to wait for I/O. It doesn't matter whether you're on a PCI Express SSD or a hard disk drive. You're going to eventually get I/O bound. So adding more threads ain't going to help you at that point. You're sitting there waiting for your hard disk spindles. One of the keys here is we are memory. But InnoDB standard buffers are 16 kilobytes. It's not that large of a data, and you know it makes sense for a hard disk drive to read a 16K chunk. In fact, some of our RAID strips are exactly 16K because of this. But we don't need that we don't need to actually perform that operation. I'll go into that in a little bit of detail. So how do we do this optimization? And I'll talk about the results in a bit. I think you'll be shocked, and you'll probably want to check our website to get the real benchmark. By changing the database backend, the page buffer handler, simply to directly access memory stored in storage class memory, and not use this DRAM caching, you know, of the page buffers, we got some pretty amazing results. Let me kind of describe what's going on here. You have this simple select. You're trying to get all the info for user ID 151. It's 160 bytes in this example. So we have all of these pages in yellow, InnoDB page 1, 2, 3, 4, 5, etc. If you're doing any sort of disk, SSD, PCI Express SSD, it doesn't matter. If the data is not already in DRAM, you're going to have to go off. You're going to do an OS call, and you're going to read 16 kilobytes, that one page. Your InnoDB is not going to make progress until that data is completely back inside DRAM. And then your processor's only going to read that 160 bytes you needed for that row. What the storage class memory optimization has done here is say, I already have all of this data available to me. I'm just going to calculate that address and read those 160 bytes. The processor doesn't transfer any more data than is necessary. And that is a pretty phenomenal improvement. We've gotten all of the optimization or all of the improvements in performance simply by getting rid of this wasted read and this I/O bottleneck. Kind of the other thing I was talking about, when you do a page buffer request, when you try to read something off a disk, you're going to go into the kernel mode, you're going to go through your ext3 or ZFS or whatever, you're going to hit your libata, and then you're going to go and actually go on the drive and then back up the stack, go back to that other kernel or kernel to user swap, 60 microseconds, which is 60,000 nanoseconds to 10 billion if you're still on a disk, which I hope you're not. What storage class memory and what the optimizations we've done at the operating system level as well as the hardware let us do is inside user space, directly access that data inside the storage class memory. So your database is stored inside that bottom block. Block storage or storage class memory. User can't tell. The database can. The database says, oh, I have this address. I'm just going to read it. A read to this device takes about, in our current implementation, it takes about 300 nanoseconds to get 64 bytes. And that's repeatable, that's parallel, anywhere, completely random. That's phenomenal. That's quite a few orders of magnitude larger than even the fastest SSD, simply because of the underlying technology and the underlying optimization of not reading stuff you don't need. Now, this is the 50 to 70x performance. You're probably, oh, yeah, sure. All right, please go to our website. We've got a third-party benchmark describing the exact database, the exact schema, the exact queries we're talking about. But the key here is the multiplicative factor of only reading what we need, as well as not doing that kernel-to-user transition, or user-kernel-user transition, enables MySQL. Without any changes in the front end. We're not optimizing the query optimizer. We're not doing anything to that. To go about 50 to 70 times faster than a SAS RAID of, I guess, 6 hard drives RAID 0. Not very fault tolerant, mind you. And 7 times faster than world-class PCI Express-based SSD that we have in our labs. That is, it's on www.viridin.com. You can check it, run it, look at it. You know, we'd actually like to get feedback. So please, send email. My email's in the front, and we'll talk about it. But the key there is by simply doing that small optimization, not touching the front, we're able to get this kind of performance boost. Memcached is another one of our initial applications. Memcached loves memory, That's in its name. This is not surprising. But for our initial storage class memory, we have a little slower writes than reads. Memcached, however, if you know the internals, they like to do lots of linked list updates, etc. That's not very good for this specific implementation of storage class memory. So what we've done is we've actually implemented a two-layer, or basically a layer 1 and layer 2 data store inside memcached. So short-lived objects or new objects start out in DRAM. As they fall on through the LRU, the least recently used queue, when they'd eventually be thrown out because of capacity issues, they actually get placed into the storage class memory. Reads of this data operate at high speeds, memory speeds. You can't tell the difference. And the key here is that you can store very small data blocks. So our tests, normally we do 64-byte objects with a little bit of randomization to get the data size so it's not all the same guy. And we store easily between 1.3 to 1.4 billion 64-byte objects inside our medium class server. Double that for our highest end product. And the key there is that it's small blocks. We don't actually have to get a very large bit of data to give you this optimization. However, there's always a bottleneck behind it. Once we start adding this extra memory, then other little things pop up. There's lots of mutexes as far as the slab locking, etc. And our guys have done a lot of code changes to memcached, and I know other people are working on this as well. The changes that we've done that are useful for the rest of the world that aren't storage class memory specific, we will be releasing to the open source community sometime soon. I don't know the exact date, but check our website. Send me a mail if you've got a question. The other key is a network interrupt handling. God, 300. We can sustain about 300,000 sets plus gets a second. Over a gigabit Ethernet port, that's actually, the networking becomes the real issue there. Even though your data is not filling this pipe, the fact that you've got these many little packets going through gets to be quite challenging. And we didn't expect this in the beginning. We figured, memcached, we're going to have to worry about memory optimization. In the end, it's a lot of network tweaks and using polling drivers and things like that, which we didn't even imagine in the beginning. Search applications were actually one of the first things we were looking at. And we're still interested in Lucene and Solar and all of those types. Applications for storage class memory, because there's lots and lots of search data available out there. Lots and lots of data to be searched, and the fact that you can randomly access it quickly is quite a useful thing. But the problem is lots of people are using Solar, which is great, but they're using Solar because they need to keep their data sets inside DRAM. And this is just the same as the MySQL sharding. You could have a whole, one server with a disk, 500 gigabytes, store it all in there, and just run, but your performance would really suffer. However, if you can put those 512 gigabytes inside a single box and access it at memory speed, which is really what you're looking for, you probably don't need to have all of those boxes sitting around, and that's going to help with your power, your OpEx issues, things of that sort. The other key here is lots of people have warm-up issues. You've got a set of queries you run against Solar when you power it up to get the database warmed up, get things into memory. It's already in memory. You turn it on, you get the same QPS as if you had it running for 2 weeks. And that's one of the other keys. It's persistent, it's there. You don't have to worry about it. Other optimizations that we're looking at, some of the data layouts, they're great for disks. They're great if you've got more CPU than memory to handle. Things like variable integers where you have to process the first guy before you can figure out what the next guy is. It's fine for that, but now that you've got all this memory, you might want to think about uncompressing it so you can do binary searches, which are going to be normally faster than the skip list searching that Lucene is doing today. There's some other locking issues as well that we're running into, and I'm sure that other people are running into that as well. But beyond just making things faster, we're trying to look at making things better. The fact that now I can access all of this data so quickly means that I can actually look at the articles or the web pages I'm indexing and compare the two and actually do a better weighting function than a number of words in the document versus the hits. Yes?
But it seems to me that what you're saying implies that some other applications can run on this box.
We are looking at it, yes.
That is to counter the notion that this is just a package memcache.
Well, our GA was for the memcache and the MySQL. We are looking at development servers, and that's kind of why I'm talking here today, because I want to get, we don't have all the answers. We'd like to hear what other people are thinking about when they see, hey, I have 500 gigabytes of memory. What can I do with it?
So the other question I have, and sorry for interrupting.
No, that's fine.
Santa Claus. It wasn't clear from the presentation which type of flash are you using? Are you using NOR flash, NAND flash?
We are using NOR flash.
You're using NOR.
We're using NOR flash right now.
You're bucking the trend that, let everybody else know.
Yes, and there's a very specific reason for that.
Understood.
NOR is random access, and that's why we can go and get you any bit of data
Understood.
in a nanosecond.
Wonderful.
So not just making it faster, making it better. Out of time? Okay. All right. Well, so in-memory computing, storage class memories here today. Check our website. Send me a mail if you got some ideas. If you got questions. Thank you very much.
You were talking about